Hi, this lecture continues the previous lecture where I showed you how to define this thing that I've rewritten called the electric potential difference around a point charge. And actually, I just realized that I made a mistake. So the idea is if I have a charge called Q1, here it is, and I was imagining it to be a positive charge, but I'll show you during this little lecture what it would look like for negative charges. But anyways, the idea is I got two places on an x-axis, and I'm imagining Q1 to be at the origin, although it doesn't have to be. But the point is I imagined having, say, an x initial and an x final, like this, and I'm wondering what is the difference in potential associated with Q1's electric field between these two places. And in particular, this was the difference between the potential of Q1's electric field at a position, say, equal to x final, minus the potential due to the same electric field, due to the same charge, right, at a different position, x initial. So it's the difference in potential between two places. So let me write this. Actually, I'm going to type it. So this is what the potential is defined for. It's defined for different places. And what sits at those places is not necessarily charged. Those places could be empty places, right? Just empty positions in space. And this is what this delta V is. So I'm imagining having a value for the potential at one place and the value of the potential at a different place, and wondering about the difference in the values, and that's delta. Delta is the difference between those two values. So what I want to introduce in this video, though, is I showed you how to understand what the difference is, but I didn't necessarily show you how to understand the values at the two places. I just showed you how to understand what the difference between the values is of those two places. So I want in this lecture video to show you a practical definition for the potential at a single place, right, at a place. And you can use this practical definition to always calculate the differences, because you would know how to calculate the individual values at one place and at another place, and then you can always get the difference yourself starting from this particular definition. So the definition is actually written in the following way. The potential of a point charge at distance r away from the point charge. So this is the potential of a point charge. It's equal to k, which is 1 over 4 pi epsilon naught, times the charge divided by the distance. So this is the potential of the charge q, and we're asking about what is the value of the potential at places r, or distances r. So r is simply the distance from Q to the place, right? Often I'm calling it a place called capital P. It's some coordinate, right? X, Y, Z. So from Q, it's the distance from Q to the place P where we want to know the value of V, right? So it's a distance. In three-dimensional space, what I'm asking you to imagine is, so here are some XYZ coordinates. Let's say this is the Z-axis, X-axis, Y-axis. Here is our little point charge Q. And if you go a distance over to here at, let's say, this P1, where this P1 is a distance R away, right? From here to there is this distance R. The value of the potential at this place is just V of R, where you calculate it this way up here, right? So yeah, but if you just stay the same distance away, like you go check this other position out here, it's called P2, but it's the same distance away, right? If it's the same distance away, you're going to calculate the same value of the potential. And if you check this other place down here, right, which seems to have maybe a negative Z value and some values for X and Y, but if it's also the same distance away, you're going to calculate the same value of the potential. But if you go, a different distance away, then you're going to calculate a different value of the potential. If you go out to a larger value of R, then your potential is going to get smaller. And if you put in smaller values of R, that is, you're checking what is the value of the potential close to the charge Q, then you're dividing by small numbers and you'll get a big value for the potential. Okay, so if we have this definition, right, it's equal to KQ over R, you know that the R value can be understood by coordinates this way. Right? This is the Pythagorean theorem in three-dimensional space, where the position P is given a Cartesian coordinate x, y, z. So we can ask what is the value of the potential at different coordinate locations. It's just k, q divided by x squared plus y squared plus z squared under the square root. Like this. So this will be the potential at a place P described by the coordinate x, y, z. But this, let me caution you really quickly, this is only if Q is at the origin, right? If Q is not at the origin, then you have to be more careful about what you mean by this distance R. So you might have to make some edits, but this to this formula, but I hope you can sort of see through the problem. But if the charge Q is at the origin, then the potential can be written this way, right here. Okay, so this is the potential at a place P, and it is very practical. So here's something that we could do, actually. So it's an interesting application. Actually, let me type it. I'm sorry to. So an interesting application of this. What if we did this? So here are multiple charges. So here is a coordinate system, let's say X and Y, and here's a charge Q1, and here is a charge Q2, and here is a charge Q3, and I want to know at this place P, what is the value of the net electric potential, right? So this is the question, what's the potential out at P? So the answer is you just add up the three contributions separately, right? So V net would equal V at P due to Q1 plus V at P due to Q2 plus V, at the same place P due to Q3. And this is the superposition principle for electrostatic potential, right? So that'll be the net potential at P. In order to continue with this problem, we need more sort of data, right? It sort of looks like Q1's at the origin, Q3's along the x-axis, you know, some distance over, and then Q2 is up on the y-axis. So in order to do this problem, right, we need to know how far is Q3 from P, and then also how far is Q1 from P, and then we still need a third distance, right? How far is Q2 from P? And if we knew those distances, the truth is it's super easy to write down the answer. So the net potential will be, it'll be K Q1 over distance 1 plus K Q2 over distance 2 plus K Q3 over distance 3. And notice we just need distances. The thing about the electric potential is the problems tend to be kind of easy in the sense that we're not dealing with vector components. So when we were talking in terms of electric fields and the net electric field, right, we used the superposition principle, but you had to do it according to components. You had to add the vectors as vectors. But the electric potential, it turns out that you can ignore the directions. It only matters the separation distances, not the directions, right, in order to calculate the potential. So just need distances, right? So here is a more interesting application. So a more interesting application is to wonder how you might do the following thing. What if I had a charged rod, right? So I have a thin charged rod, and then here is a location P, some distance away from the end of the charged rod, and for simplicity, let's only think in terms of the x direction for a second. So the charged rod is along the x direction. It has a linear charge density lambda, and I can imagine small distances where, actually, let me do it this way, where there is a small amount of charge, which is some distance away from the position P, right? And I can imagine what is the potential at P due to all the small charges along this charge density. So each small charge dq contributes a small potential dV, right? So this is not d volume, but d potential. So a small calculus contribution called dV at P. And so the net potential at P is the sum of all the small contributions. Each small contribution is a K times that small amount of charge divided by the distance between the small charge and the position P, right? So this integral I have to figure out how to do. So here's this problem again. So I got this charged rod. Let's imagine that the end of the charged rod is at x equals to 0 over here. At x equals to L is the end of the rod, and some more distance out here. So this is, let's say, actually, we can do this. Let's say that this right here is a distance called capital D. Excuse me for using so many symbols, and we'll put a linear charge density along the rod, and we can imagine that this is all happening along the x direction, right? So this is x equals to L, and this is x equals to L plus D, right? So that this position is the position P. And so the net electric potential over here at P, due to all these charges dq, oops, right? It can just be written down as, I'm going to integrate over distances, right? So the distances are, they go from, say, if we start at the near end of the rod, you can see that the distance starts off as capital D and then gets as large as L plus D. So we'll take our distance, right? We're going to do K dq over the distance, and the distance little d is going to start, from this value, this value, which is the small value of distance, right? That's the small distance, and then we're going to go over to here, which is a little bit further away, to here a little bit further away, to here a little bit further away, etc., right? So we're going to go from D up to L plus D. All right. Yeah. And so, cool. So this is, unfortunately, excuse me, I'm going to erase this, and I'm going to call that distance x. And I'm so sorry to change that right now, but I'm going to do it. So I'll put the distance x, and I'm going to integrate along those x values, right? Yeah. Okay, so when you do this, Okay, yeah. So dq is lambda dx. So v net equals integral from d up to L plus d. And then it'll go k lambda dx over x values. And when you integrate this, oh, check it out, right? You're going to have essentially this integral, which you'll remember is the natural log. And the way the natural log works, and this is kind of strange, I'm going to show you something that actually has something wrong with it. It's the natural log, right, of x evaluated at the bounds d and L plus d, right? So if you just write this down, this is actually kind of strange. As an aside, if you have a function, natural log of x, x is actually not allowed to have units, right? So the argument of the natural log is actually not supposed to have units. We're going to pull a fast one, though, when we do this integral, because I'm going to do the fast one. It goes k lambda and then natural log of L plus d, right, minus the natural log of d. But the fast one, right, so the problem with this is that the arguments of the natural log have units, like, because they're distances, right? So you're not supposed to have that, but we're saved by the fact that we have a subtraction. So let's take one more step. So the difference between two natural logs is actually the natural log of the quotient. Right? So this right here is considered the net potential for this problem. So the potential at P, due to all of these charges, is this thing. Okay, cool. So what I've shown you in this little lecture is we started with only a definition for a difference. But then I said, why don't we define not the difference, but let's define the value at the two places. And if you look at how this looks, there's the k, the charge, the distance, and that's what actually sits here. The k, the charge, and the distance. The k, the charge, and the distance, and this is the difference between the value at two places. So this thing is going to do what we need. So we can use this thing with point charges, which I did here. Right? With point charges, we could talk about the net potential, which is just the sum of the potential of each point charge. Right? Can you see this is the summation? So what's happening is I'm using a summation symbol, right? But then I told you, well, if you can imagine it being in terms of a summation symbol over points, we can update it to using calculus. In particular, we can, instead of doing a summation symbol, we can do an integration symbol instead. So I asked you to think of the action of adding up the total potential as the integral of a bunch of small parts of the potential, where each of the small parts is due to a small charge. right? And so I showed you an example of calculating the potential of a charged rod. And it comes out with this funny formula, this natural log business, but that is what it is. Okay, thanks for listening.